Okay, guys. So let's begin with Igor Brandão's thesis defense, master thesis defense. First of all, thank you for all the members of the jury for coming here today. And please, Igor, you can start now with your presentation. You maybe share your screen.
And can you all see my screen, see my slides here?
Yes.
Okay, perfect. Just go to full screen. Okay. So my name is Igor Brandão. Today I'm going to present my master's dissertation defense. First, I'd like to thank the dissertation committee for being here today and accepting the invite. And well, my dissertation was entitled Harnessing Optomechanical Interactions from Trapping Organisms to Entangling Nanospheres. And I believe the first thing that I must present you is what is the field of optomechanics. Well, it is the research field that studies interactions between light and matter. As we know, since the beginning of the 20th century, as it was famously demonstrated by Einstein, we know that light can carry momentum, and thus, through transfer of linear momentum with some mechanical system, it can imprint some radiation pressure force. Okay, it has been experimentally demonstrated that from suspended microscopic mirrors of about some mass of around a few grams, down even to ultra-cold atomic gases or ultra-cold single atoms of a mass of about septograms, the interaction can influence their motion. The system I will be talking about today, which was the focus of my dissertation and research for the past 2 years, are presented here on the right, which are essentially the optical tweezer, which is a highly focused optical beam, which we know that can optically trap dielectric particles close to its focus, as depicted here, and optical cavities, which are highly reflective parallel mirrors, which when we shine a laser into them, it can store some resonating electromagnetic field, which can couple to the position, for example, a mechanical object here depicted as one of the antimirrors of the cavity, which is free to move under some harmonic potential. Okay, but more than a transfer of linear momentum, we also know that light can carry energy and angular momentum, which can also be transferred to matter. For example, we're considering a coherent scattering setup, which we'll talk about towards the end of the presentation. We know that if some optically levitated particle is placed within an optical cavity, it can scatter some of the optical tweezer's light into the cavity, which carry away some of its energy. And last year, this was shown to, for example, achieve ground state cooling of a nanometer size of silica sphere. As just another brief example, we can consider some 2 silicon nanospheres that are glued to each other and placed within an optical tweezer, which carries some angular momentum. It has been shown in 2018 that the transfer of angular momentum from the optical field into the mechanical system could spin the system up to about some gigahertz rotation, which is, at least for me, incredibly fast for a mechanical system. But okay, what are some applications of these optomechanical couplings? Well, first off, optical tweezers, as we'll talk about in a moment, we know that it can achieve some very high precision, very high resolution displacement measurements of about 1 picometers in the movement of the levitated particle. And as for example, Gaussian optical tweezers create a linear force in the particle, this can translate into a force sensing of about femtonewtons. So we can have a really high resolution on the position and force that a levitated particle feels. We can also generate some very interesting quantum states. We can, for example, there has been experimental implementation generating mechanical entanglement between centimeter spaced apart particles that was generated by a mediator optical field. There has been theoretical works considering if optomechanical coupling could generate, for example, spatial superposition of living organisms. And as I have just said before, we can perform quantum control over matter, as for example, the ground state cooling experiment last year. So when we combine all of this, the field of optomechanics becomes a great playground to test new physics. For example, witnessing quantum effects in the gravitational fields or testing collapse models of quantum mechanics. Okay, this is just a brief introduction. Let me get started on the specific research I performed the last 2 years. I'll start talking about optical tweezers, which, as I have said before, are highly focused light beams that through transfer of linear momentum can exert radiation pressure force on mechanical objects. Here on the left, I have shown a Gaussian beam, which is optically trapping some dielectric nanosphere close to its focus. As we'll see in a moment, if we have some dielectric particle whose refractive index is greater than the medium's refractive index the particle is in, a Gaussian beam close to its focus can 3D optically trap the levitated nanoparticle, and this allows for a great number of applications. For example, the displacement, high force resolution, which we had before. We can finally control the position and rotation of the particle because of the position of the laser. And as the levitated particle is not clamped to an external mechanical system, the levitated particle achieves an exceptional environmental isolation because no unwanted vibration from the external system is translated into the movement of the particle. But okay, what can we optically trap? Well, this ranges from about a single or a cloud of atoms going to some nanometric silica spheres and up to micron-sized living organisms. The usual wavelength that is used in optomechanical experiments to trap these particles are used in the range of the visible to the near infrared, which translates into 400 nanometers to about tens of micrometers. And depending on the relative size of these trapped particles and the wavelength of our trapping tweezer, we can define three different regimes that we use to model the interactions of the particle and the optical field. These are essentially when the particle is much smaller than the wavelength, when this of an approximate size, and when the particle is much bigger than the wavelength of the trapping beam. We will not get into details of the geometrical optics, but I would like to give a brief introduction to this topic for these two regimes. Okay, let's start talking about when the particle, when this, for simplicity, we consider a spherical particle with radius r, is of about the wavelength of the optical beam. Here we have a figure of a Gaussian beam, of an incoming Gaussian beam, which interacts with some dielectric particle, and the outward going beam is very altered by the interaction of this mechanical system. Through the Lorentz-Mees scattering theory, we can mathematically describe the angular momentum of the incoming beam, the outward going beam, and from this difference momentum and considering the conservation momentum from the total system, we can find the total optical force that arises in this particle. But when we consider smaller particles, for example, a particle with a radius that's about half of the wavelength of even smaller, the outward going beam becomes increasingly less altered by the presence of the particle. And when the particle is much smaller than the wavelength, we must consider another different regime to calculate the optical force that arises in it. For example, when we consider dielectric particles, which was the focus of my dissertation, we can approximate the particle by some electric dipole that is embedded in some electrical field of the trapping beam. And when we work out the mathematics of the Lorentz force applied to this particle, we end up with two forces. Now I just must make a brief comment that I always through this presentation consider linearly polarized light beams, so there is not a third force here. But okay, these forces are essentially, well, the scattering force here is essentially some constant proportional to the intensity spatial profile of the beam, and it points towards the direction of the propagation of the beam. Essentially, you have some particle, the light beam will hit we can say that it hits the particle and tries to move it around. And we also have the gradient force, which will be, at least for me, more interesting, because it points in the direction of the gradient of the intensity of the light beam. And so some particle placed here, we want to feel a force that moves in the direction of greater or lower increase of the intensity. But we have a catch, which is that there is some parameter here in parentheses, which may be positive or negative, and so the particle will want to move closer to the higher intensity regions or away from it. This n parameter here is given here below, which is simply the refractive index of the particle divided by the refractive index of the medium. And so when we have a particle with higher refractive index than the medium, this points towards the higher intensity region. And for the case, for example, of such particle in a Gaussian beam, the particle in position here will always feel a gradient force that points towards the focus of the beam, where we have a higher intensity. However, when we have a particle with lower refractive index than the medium, the particle will try to run away from the high intensity region, and this is where the case where we're interested in this section. Okay, just a brief summary, a very, very brief summary. What I want you to remember from this slide is that the intensity profile of the beam, the spatial intensity profile of the optical beam dictates the kind of force the particle will feel. So when we consider what will happen, what the force the particle will feel when we use some structured optical beams. Here, for example, we have a Laguerre beams shown at their focal plane, which are essentially a complete set of solutions to the paraxial electromagnetic wave equation. Okay, for example, we may wonder what would, the Laguerre beams have two parameters that dictates the form of the beam. But essentially, what we want to say here is that if we choose some different structured optical beams, we can have some different optical potentials that the particle will feel. And so, with all this knowledge, we thought, okay, what if we consider some Gaussian beam out of phase with some Laguerre beam, such that the Laguerre have a L equals 0 and some P, here depicted with P equals 1 for simplicity. Well, this generates the so-called bottle beam, which is essentially a bottle-shaped beam. And what I mean by that is that in the focal plane, it has this intensity profile, but along the propagation of the beam in the longitudinal direction, this beam has a very bright intensity, some dark focus depicted here in the center of the image, and afterwards it has a very bright intensity once again along its symmetry axis. So if we have some particle with lower refractive index in the medium, some particle placed here would not be able to leave this high intensity boundary. I have here to show below a video of various cross sections along the propagation direction of the beam, and this is precisely what we have. We have some very bright intensity, it then becomes some very dark focus, and then once again becomes a bright region. And so, let me play it once again. A particle placed close to its focus here, in all directions would be surrounded by light and would not be able to escape, as it would be free to move until it hits the high intensity boundary, and then to go back again into the center of the bottle beam. Another way to visualize this beam is looking at its intensity profiles in the radial and axial directions. Here in the radial and axial directions, and we clearly observe some dark focus where there is no intensity, surrounded by very high intensity boundaries. And from the distance between these boundaries, we can, for example, define the width and height of the bottle, the distance between these, for example, these high intensities and along the longitudinal direction. Okay. And if we consider a particle in the dipole regime much smaller than the wavelength of the beam, we can simulate its trajectory by considering the overdamped Langevin equations for its equation of motion, and simulate the trajectory the particle will follow which are shown here, where every blue dot is one position along the trajectory of the particle. Okay, so what we see here in this blue plot on the right is that effectively the particle may start in the center of the bottle beam. It may walk around because due to collisions with the environmental gas, but it does not leave some very constrained region which is within the boundaries of the bottle beam. In the intermediate regime, we may consider how, for example, living organisms with a much higher radius of dimensions may feel this force. Well, why are we talking about living organisms? Well, because when we have a bottle beam, our interest in the bottle beam is because at its focus, there is no light, and so there is no excessive laser damage into the optical field that heats up the cell. So the bottle beam can be a good way for us to trap living organisms without excessive damage. Here we have some Mycoplasma cell depicted just to show that we can live well within the width and height of the bottle, depicted by W in H. And we see that both in the radial and axial directions, the force that this particle suffers is approximately linear and restorative force, and so the particle will probably be trapped here within the bottle. Okay, let me just make a brief summary of everything that I have said in this section. Essentially, we know that optical beams can exert radiation pressure force on nano-sized and micron-sized particles. If we have some Gaussian beam with a bright focus, it can trap particles with higher refractive index than the medium. And if we have, for example, a bottle beam with a dark focus, it can trap particles with a lower refractive index than its medium. Okay, but that's enough of optical tweezers. Let's talk about now optical cavities. Okay, as I have said before, optical cavities are essentially highly reflective parallel mirrors, which can store some resonating electric field within it. And so the optical field within an optical cavity is essentially, I'm sorry, let me start over. So the resonating electromagnetic field within an optical cavity can live in the discrete set of resonant modes with some associated resonance frequencies. Okay, this explains to us how the electromagnetic field inside the cavity exists, but how can it couple to matter? We'll consider only a single mode within the cavity for simplicity. And if we consider, for example, one extremity of the optical cavity be free to move under some harmonic potential, every time this mirror moves, it will alter the length of the cavity, and by consequence, will alter the resonance frequency of the cavity. If we consider some small amplitude of motion for this mirror, we can tailor approximate this expression up to linear order. And when we consider the quantized Hamiltonian that describe these systems, well, we have some harmonic oscillator from mechanical systems, so we have this harmonic oscillator. And the quantized electromagnetic field can be approximated as an harmonic oscillator, whose frequency at this case is dependent on position mirror, which in this approximation simply results in an additional term for the Hamiltonian, which is a coupling term between the number of photons within the cavity and the position of the mechanical oscillator. If we consider the Heisenberg equation of motions for this end mirror, we see that it essentially adds a force that's proportional to the number of photons within the cavity. And so both the mechanical and optical modes are coupled. But there are other systems which also have the same Hamiltonian and thus the same closed dynamics. We can have, for example, ultra-cooled atomic gas clouds trapped inside an optical cavity, some levitated nanoparticle, some optically levitated nanoparticle trapped inside an optical cavity. And if the optical tweezer here is finely tuned with the optical cavity, the Hamiltonian that describes these systems is essentially dispersive Hamiltonian described here. And also we consider some membrane placed inside the cavity with many vibrational modes. Okay, I want to make a brief comment now, take a step back and talk about this system here. Because we have a work called Directed Graphs Interferometer, where we studied precisely this system, where we have some optical cavity, here shown as these blue blocks, and some dispersive element, which may be some membrane. And at this work, we show that any interferometric setup, as shown here on the left, may be associated with some weighted directed graph, which contain all the information of the transmission and reflection of the optical field within this interferometer. For example, an optical cavity with a membrane inside it. And sorry, I'm not going to have time to talk about the details here, but after some simplification rules that we may apply for these directed graphs, we may result in a very simplified graph which relates both the input and the output of the cavity, whose weight of the edge that connects these two vertices carries away the information of how much of the input electric field results in the output electric field. Okay, it is just a brief comment. I will not dwell on the subject any further, unfortunately. But if you go back to the optomechanical system, we may want to look at this system, for example. There is the same system of the last slide, where we have some optical cavity, we have some membrane or mirror inside the cavity, and we will not allow this mirror to perform photon transfer from one side to the other, from one side of the cavity to the other. Okay, so what we will have essentially is one optical cavity here on the left and another optical cavity on the right. And as this mirror moves around, it may, for example, expand one cavity and contract another, and may correlate these optical fields. Well, as these are essentially optical cavities at its sides, this is essentially the same analogous system to that I have seen before, and the Hamiltonian is completely analogous to what we just seen 2 slides ago. Of course, as we have some analysis for other mechanical systems placed inside the cavity, we can also consider some levitated particle or atomic gas cloud inside an optical cavity with 2 different optical modes within the cavity, which generate exactly the same Hamiltonian. Okay, but why are we interested in this system? Just let me a moment to drink some water. Well, there is this article by Thiago and Vedral from 2017, which proposed a very interesting argument. And let me go back to that slide to use this figure. It stated that if some subsystem A, if a global system starts unentangled, and subsystem A never directly interacts with subsystem B, but each of them locally interact with some system C, in this case for us, the mirror inside the cavity. If at some moment in its dynamics there appears some entanglement between A and B, we can certainly say that the mediator between them must be non-classical. Okay, of course, Marleto and Vedral were trying to use this argument to witness some non-classicality of the gravitational field. And for this system, we'll just make a brief comment that there is this article by Bose and Krishnanda, which are very interesting on the subject, but I will surely not have time to talk about this. But we may wonder, can we use this argument to see if there will be optical entanglement in this system, and thus assert that there is a non-classicality for possibly macroscopic harmonic oscillator? And well, the first thing that we did was to find the unitary time evolution operator for the system, which is depicted here, which is essentially comprised of a free evolution term, some optomechanical entangling term, which connects the optical fields with the mechanical oscillator, and some optically entangling term. Okay, so we expect that there will be some optical entanglement in this system. And as the argument requires, we need initially separable systems, separable global states. And from the form of this time dependence we have here, we know that at some time, if there is optical entanglement because of the form of B of t, there must be some depth of entanglement, and the same applies for the optomechanical entanglement. But how do we know that there will be some entanglement in the system? Well, we can use the Duan criteria, which is essentially a criterion of separability for continuous variable states. Sorry. Okay, I will not have time to dwell into the mathematical formalism, but essentially, if we consider some quantity dij between modes I and mode j, which is essentially an average of the idempotent growths and variances for some IPR operators, we can say that, okay, if modes I and j, for example, the optical mode A and optical mode B, are separable at some instant of time, then we must have dij greater than 1. But the opposite of the sentence is true, and if dij is less than 1, we can know for certain that these modes, for example, the optical modes, are entangled. Given the initial state that we assumed, which was some populated optical cavities and a thermal state for the mechanical oscillator, we were able to find analytical expressions for the Duan criteria. And we were able to also find some parameter region. We were able to find a parameter region which is connected with a realistic implementation with an ultra-cooled atomic gas cloud inside the cavity, which allows for optical entanglement. And so for these parameters, we have this curve here, and we will want to look at the topmost plot, with the Duan criteria within the optical modes A and B, which is in yellow, which is a quickly oscillating term, with its envelope given in blue. But we can clearly observe that at some times, the Duan criteria is certainly less than threshold 1, which is shown here in a dashed black line. And at those moments, we can certainly say that there is optical entanglement, and through Vedral's argument, we can say that the mechanical mediator is non-classical. Okay, I've said a lot of things. Let me just summarize. We know that optical cavities can store resonant electromagnetic fields, which in turn can exert radiation pressure force on mechanical objects. We have seen that there is a plethora of mechanical objects which can interact with the optical field. We have seen that the closed dynamics for this system is entangling, and for the setup we were considering, the appearance of optical entanglement can infer non-classicality of a potentially macroscopic mechanical oscillator. Okay, let me back into the last part of my presentation, where I want to combine the optical cavities and optical tweezers and study this coherent scattering setup. Okay, let me just have a glass of water for a second. As I have said before, in the coherent scattering setup, we have some optically levitated nanoparticle placed inside an optical cavity. And now the light matter interaction comes from the scattering of the tweezers into the optical cavity. And well, this allows for a very strong light matter coupling, which has been seen experimentally. This has allowed for 3D cooling of the levitated particle motion. And along the cavity axis, it has even generated emotional ground state cooling. The particle has been cooled very close to the ground state for lower than 1 phonon occupancy. It has also been theorized that this will generate mechanical squeezing of the particle's quantum states. And the system I am interested in is analogous to this one, which is many levitated nanoparticles, and here we have an arbitrary number of levitated nanoparticles placed inside the same cavity. And the question that I want to answer is, okay, the coherent scattering of photons from each particle in the cavity will generate an optomechanical interaction between each particle in the cavity. But can the optical field within the cavity mediate some entanglement between the mechanical systems? Well, in the case of a very high vacuum environment, this has been studied by the group of Klaus Farnberger, And they've seen that in this case, where we have almost no interaction with the residual gas inside the cavity, and everything in the system starts in the vacuum state, yes, there will be appearance of entanglement. In the steady state, in a more challenging scenario for appearance of entanglement, it has been shown before that this entanglement will only be generated for a very cooled down environment. But I want to answer is, okay, maybe in a moderate vacuum, which is more challenging, we can have some entanglement before the system achieves the steady state. The first thing that I need to do here is to describe the Hamiltonian for the system, which I can do using the dipole approximation, which I have talked before on the optical trapping. And I'll give just a brief introduction here for the quantized case. Well, the Hamiltonian in this case will be simply the free energy of the nanoparticles, the total energy stored in the electromagnetic field, and we'll also have some interaction energy between the particles in the electric field, which is given essentially for each particle as the intensity of the electric field at the position of each particle. Okay, so the next question is, what is the total electrical field? Well, we'll have each optical tweezers, we'll have each optical tweezer's electric field, we'll have the intracavity field, and we may also consider the free electromagnetic field inside the cavity in some vacuum state, for example. As I shown in the dissertation, the interaction with the free field results in a negligible interaction energy, so we can skip over this interaction for the moment. And another thing that we'll assume is that we have no overlapping tweezers, as this would generate a direct interaction between the particle, and it is, well, experimentally challenging. So it is really well within reasonable conditions, I assume. So after we Taylor explained the electrical fields around the mean position of the nanoparticles in each optical tweezers and move into a rotating frame, we have this Hamiltonian here, which I'll just speak very briefly. Essentially, the first line dictates the harmonic oscillators of both the optical field and the mechanical oscillator. We have some constant driving in both the cavity field and the particles, but the interesting coupling terms are presented here in the last three lines, where if we may recognize this term, which is essentially the number of photons within the cavity times the position of the particle, and this is simply the dispersive coupling I have talked before in the last section. The last two lines are actually the coherent scatter interaction, which couples the cavity's position and momentum quadratures with the positions along the x and z directions of the particle. And let me go back just a few slides here. If you look at the schematics of the setup that we are interested, we see that x01, x0n are the position of each particle along the cavity axis, and theta j is the polarization of the optical tweezer relative to the optical cavity. Well, why are these interesting? Because first, we see that the nose dependence of the polarization of the particle, there's no dependence of theta j here in this line. So if we choose the optical tweezer to be aligned with the optical cavity, or in other words, we can kill this sign, this and this sign, we can completely kill the coherent scatter interaction. Or if we want to, for example, place the optical cavities as some nodes of the optical field within the cavity, we can kill these cosine terms here, this sine of 2 k is x0, and this cosine, and we end up with only the coherent scatter interaction, which is precisely what we want to study. So by properly positioning the particles, we end up with this Hamiltonian here, where I have just opened up the position operator of the particles into some annihilation creation operators. And the unitary dynamics of the system can be dictated by the Heisenberg equation of motions for the systems. Here we are using the dimensionless quadratures for both the cavity and the particle. And when we can talk about now the entanglement in HB partition of the system, if you look at the logarithmic negativity. which, although I really like this subject, I will only say here that it's a entanglement monotone. And so each time we have a non-zero logarithmic negativity, we'll have some entanglement in the system. And if the logarithmic negativity rises, we'll have even a higher entanglement that we partition. Okay, so in blue here, we have the logarithmic negativity for some bipartition system. We're only considering 2 nanoparticles in a unitary dynamics. And we have clearly observed the cyclic dynamics of periodic birth and death of entanglement between the optical cavity in particle 1, optical cavity in particle 2, and more importantly, between each particles 1 and 2, and we clearly observe some generation of mechanical entanglement. Okay, we know that this generates mechanical entanglement, and what will happen when we consider a realistic implementation following an open quantum dynamics. Okay, this can be simulated to a set of quantum Langevin equations, which for one hand, when considering the intracavity field, dictates how the external electromagnetic field through the cavity may interact with the intracavity field to some leaking of the cavity for some transfer of photons from one side to the other of the cavity. And essentially, this results in some damping terms in the equation of motions and some stochastic noise that acts on the particle. For the intracavity field, the stochastic noise has zero average and is delta correlated in time, at least for the regime I'm considering. And when we have some levitating nanoparticle, it may contact with some residual gas that's within the vacuum chamber where the system is in. And each of these gas molecules may dampen the particle motion as it tries to move around, and may imprint some random kicks on the particle's position. And this is modeled by adding to the Heisenberg equation of motions through a damping term and a stochastic force term. And when we consider the residual gas to be in some thermal state, the stochastic force is not necessarily delta correlated in time, it's not Gaussian, but in the regime of a very high temperature environment, this force can be approximately delta correlated, which is the regime we're interested in. It simplifies our calculations. So, considering these modified Heisenberg equations with modified dynamics, we end up with these logarithmic negativity curves in blue for the same system of 2 particles, now in a cryogenic environment, such that we don't have much interaction with the residual gas. The main point here is that we clearly observe that there will be some loss of mechanical entanglement in the steady state, and the cyclic dynamic of mechanical entanglement has died out. For the entanglement between the levitated particles now only exists for a brief moment in time, and it completely dies out and remains, and there is no entanglement in the steady state. But we can change this entanglement dynamics if, for example, before the experiment can cool the particle down from a very close to the ground state, which we have a bigger maximum logarithmic negativity, sorry. Or if we can create some stronger light matter coupling. Here I've shown the logarithmic negativity involving time, right, for various different optomechanical coupling strengths. We observe that for low coupling strengths, we have no appearance of mechanical entanglement. But when we increase this coupling strength, for example, let's say here, well within the the strong coupling, where we have a coupling higher than the mechanical frequency, we not only observe a higher entanglement, but its death and revivals. And so we start to recover the unitary dynamics. As a summary, we observe that levitating nanoparticles can interact with the scattered photons into an optical cavity, creating some strong light matter coupling. Depending on position and polarization of the trapping beam, we can choose which kind of interaction the particle will have with the intracavity field. And even following open quantum dynamics, I'm sorry if I forgot to say that in this slide we're considering now a room temperature environment. so even a more challenging environment. But we also see that even in a room temperature environment, we may have mechanical entanglement of spatially separated particles. Okay, this is a very brief summary of my presentation, of my research for the last 2 years. And I wanted to close this presentation by giving a very brief outlook on some possible future research directions. In 2019, there were these two nature communications that really caught my attention. On the left here, the system they studied was two mechanical membranes dispersively interacting with some intracavity field, each of them coupled to its own heat bath, such that one was a hot heat bath with a higher temperature to the other one. And in this system, they experimentally verified that heat would flow from the hot heat bath into the one of the mechanical system. The optical field would transfer some of this heat into the other particle. And it will move around to the other heat bath. There was this alternator communication, which studied somewhat similar idea, where they consider two spin half systems, each one in a thermal state, and with no initial correlation between them. And after they interacted, it would, as expected, it would flow from the hot to the colder particle, and it would eventually thermalize. But when exactly this situation happens for initially correlated systems, so that we have some correlated systems, each on a local thermal state, given when the particle interacts, some of the correlation in the system would be consumed, and heat would flow from the cold to the hot particle. And we would end up in a situation where the cold particle would end up colder, and the hot particle would end up hotter. I would like to combine these ideas into an optomechanical situation where we might have some two mechanical particles in a coherent scattering scenario, where we would have, for example, one particle in a red detuned optical tweezer relative to the cavity, and another in a blue detuned tweezer relative to the cavity. Well, at least I'm interested in this setup because I expect that the scattering of photons would take away energy from this particle, heat up populate the optical cavity, and this could be transferred into the other particle. And maybe I could play with some appearance of mutual correlation, or there will be some parameter region where maybe this kind of reverse the heat flow could occur. But this is in the future. Okay, I would like to close this presentation by thanking my advisor, the dissertation committee, for being here today, PUC-Rio for allowing me the opportunity to conduct this research, and the funding agencies Bipartite, Serra Pilheira, and CNPq. Once again, thank you.
Okay, Igor, thank you very much for your dissertation presentation. So now we pass to the questions. And as is traditional in our department, as a matter of fact, I've never seen any department differently in all my academic career. There's this tradition that we start with the jury member that is furthest away geographically from PUC. So this is Mauro Paternostro. It's an honor to have you here, Mauro, and we're happy to hear your comments and questions for Igor. Please carry on.
Thanks a lot. Okay, so geographically far, but as I always say, my heart is in Brazil, right, guys? So I'm close. Igor, thanks for the presentation. Very comprehensive, very well done. And let me start with the good news first. Okay, and the good news is that I really enjoyed reading your dissertation. I think it's a conspicuous work. Very well written. Say I really had to work hard to find a typo or something like that. So, and I only found a few. So it's overall a job very well done. And somehow the quality of the writing is reflected in a very nice presentation as the one that you just gave. Now, because I've been asked to be nasty, I'm going to ask you a few questions. Okay.
Of course.
So let's start really broadly and then maybe narrowing it down to a few more specific queries. Now, if you look at the body of work that you have done across your degree, and the amount, say, the work that has been reported in your dissertation, put a critical hat on top of your head, and can you tell me which part of that work you are most proud of?
Well, personally, I'm very proud of the coherent scattering description of the coherent scattering setup, because I studied from the beginning of the foundation of this kind of interaction, from the Hamiltonian description, even down to its open quantum dynamics. And I'm really proud to have found that there may be mechanical entanglement between levitating maybe millimeter separated mechanical systems, which may survive even a room temperature environment under realistic parameters.
Okay, and this is understandable. I mean, fine. Every time one gets a non-zero function, right? So that's good news when you're looking for, especially when you're looking for entanglement. But see, I've been, as you might know, I've been working on optomechanics for a bit of time, and every time my problem is, so the struggle is, right? So you find mechanical entanglement. Okay, so you get you get a non-zero logarithmic negativity. You get whatever non-zero, so whichever non-zero measure of entanglement you might consider, or you might want to consider. What is this entanglement useful for?
Well, first, I believe the first application that comes to mind is that using the Pedral's argument once again, and saying that the electromagnetic field within the cavity may be non-classical, but I believe that's not too exciting. When we consider that mechanical entanglement as maybe a resourceful platform for, I don't know, maybe some quantum networks or some, well, quantum entanglement is completely non-classical, so we must maybe use it to assert some non-classicality of the mechanical oscillator, but I can believe I can see much more applications in this one, at least at this moment.
Let's say,
well,
go ahead, sorry.
No, please continue.
I mean, if I really want to be nasty, there are many other ways in which I can infer, say, non-classicality of a mechanical system, rather than looking for something that is incredibly fragile, very rare, like mechanical entanglement, no? And at the end of the day, what matters? So why would that be important? Entanglement has been seen in many other systems that are easier to manage, easier to control, more clean. So why are people so fixated, some people, so fixated with mechanical entanglement, or entanglement that you can see in this set of, in this, say, platform, in this sort of framework?
Well, for the system considered for a coherent scattering setup, we have about 100 nanometer particles, and so these well, very big systems for quantum mechanics, and made up of I don't quite remember the number, but thousands and thousands of atoms, and observing quantum correlations and clearly non-classical states may be some interest to the test of quantum mechanics in higher parameter regions, very massive and bigger particles, and test. So we can use this to test new physics, for example. Well, at least this is what most interests me.
Are you aware of any studies along this direction? So making use of these, say, macroscopic system to look into some more foundational questions?
There is, I believe, a 2013 Nature Physics, I don't remember. There's an article by Marcus Acomai we reported mechanical entanglement between centimeter-spaced mechanical oscillators. And well, I read that dozens of articles by you on mechanical generation of entanglement, so I'm very anxious now, so I won't be able to cite any of their names, but I can certainly say that I've read research on this topic.
Okay. Right. So now you told me why you are. So which part of your work you are most proud of? Which part did you most enjoy, say, working on? Not necessarily the part that you are proud of is the part that you enjoyed mostly working on, no?
I believe, well, I really liked studying the quantum Lagrangian equations. I think it was very nice to see from a really reasonable setup. We can originate somewhat simple equation of motions. I really liked studying, but what I most like probably would be either the Gaussian quantum states, which because such complicated systems for some reason become really simple. And I really liked, let's just move the slide here. Oh no, I believe it's this one. I really liked to work with the direct graphs because it was a very new mathematics to develop, and they have never seen such a, oh, okay, we can end up with very nasty graphs, which was a simple way of explaining these systems. I really enjoyed like working with this one. Okay.
Still digging into say the higher spheres, so to say, no? So high level. What is the contribution of your work to the state of the art? So how are you pushing the boundaries of research in the various strands that are touched upon in your dissertation?
Okay. First, when we studied the optical bottle beam, okay, this is a slide. We've seen that okay, it is possible to, well, at least numerically, as a theorist can, how much a theorist can say, that some living organism to be trapped within some laser beam without excessive damage, which is a big problem when we considering Gaussian beam. I find this very interesting because we can start to study some mechanical properties of living organisms. Here, when we consider mechanical entanglement, let me get the setup. I believe it's here. When we consider non-classicality, I was very happy when I found that okay, these can actually be used to observe non-classicality of tens of, I believe it was 50,000 atoms in a single time. And so I believe this was another significant contribution where we could observe. It depends on the definition, but somewhat macroscopic mechanical systems. And following the same idea, I found very pleasant to find a physical situation we could actually be done in the laboratory and observe mechanical entanglement. So what I'm most proud of is finding realistic implementations to where one can observe the effects I was looking for. That I believe is the greatest contribution.
Okay, let's stay there, right? So let's stay more or less on this slide. See, if I look at the bottom right plot, no, there are two. So these are the two temperatures for the system. Say, in the blue region, in the blue colored region of the plot, really the dark blue one. Or in the topmost one, right? So again, in the blue colored region, where you don't observe up really in the zero entanglement region. Okay, so where you don't observe entanglement, do you have a classical system?
Okay, that's a good question. Well, we will not observe entanglement. Well, at least we have not sure if there's entanglement because zero negative logarithmic negative does not imply non-existence of entanglement. But we will have some particles that are cooled down to the below 1 phonon occupancy. Well, let's see if the distribution will not be negative to Gaussian. I cannot certainly say at this moment if there is not, but a lower than 1 phonon occupancy for me, it's a good sign that we're close in the quantum regime.
Right. Can you say your your temperature is not that low, so very much likely you say in that region, so very much likely you will not be at the low occupancy level. I mean, you will have some phonons in these oscillators.
I'm sorry, Mauro, if I may add, here we are showing the phonon occupancy.
Yeah. But that's definitely not small enough to say you are in the ground,
yes.
state, so to say. But say you have a thermal state of small occupancy, mean occupancy, but nevertheless a thermal state. Well, no, not necessarily. That's not necessarily the case, and this is indeed my point. Say, is quantum correlations coincident with entanglement?
Are you asking if the theorem form of quantum correlation is entanglement? Is that the
Precisely.
question?
If
my question, another or general form of quantum correlations that are not classical.
That are not classical.
Yes, for example, quantum discord.
Perfect. So I bet my 4 years old son's shoes that even in the region where you don't observe mechanical entanglement, unless the state that you are achieving is the tensor product of two thermal states, you are going to see some non-zero. You're going to see non-zero discord. Okay, so you are going to see non-zero quantum correlations. So what I'm saying is that in the analysis that you have reported on the mechanical entanglement at room temperature, very much likely the news that you have, the good news that you have, are even more than what you are reporting. Because even where you would have zero mechanical entanglement, you might have a non-zero degree of quantum discord. There is a small theorem proven a few years ago that shows that basically only if your covariance matrix, if the covariance matrix of your system is fully diagonal, right? So basically only in the case where your state is isomorphic to a thermal state locally, right?
Yes.
You have zero discord. Even if you take two thermal states and you mix them at a beam splitter, you're going to get a non-zero Gaussian discord. Okay, so there might be something more that is hidden there and that you are not seeing simply because you are looking at a very tough indicator of non-classicality as entanglement. Now, keep on digging on entanglement. No? So can you go into your beautiful plot where you have the Yuan criterion for the three different pairs? That's it. Okay, so if I look at this plot, can you tell me something about tripartite entanglement for your system?
Well, we can certainly say that there is mechanical entanglement at some times between every bipartition, but formally, I cannot be absolutely sure that there is tripartite entanglement in this system.
Right.
At least
so
I am not completely sure to say that there is.
Sure. If I look, for instance, at a time, I mean, I can pick up other times, okay? But I don't know, because my brain works in a strange way. No, just after, say, omega t equal to 70, no? So close to omega t equal to, move a little bit on the right, yeah? That's it. So if I move vertically from that point on, I have a bipartite entanglement. So I have a bipartition between, now I forgot which are the B and C, that is non-zero, right? So you go below one, yeah? So you have B and C that are entangled,
okay.
A and C that are entangled, and that's fine because it's a symmetric system. But then you have a big peak, big negative, let's say below one peak in the AB one.
Yes.
So all three bipartitions are inseparable at that instant of time.
Yes.
That is signature of tripartite entanglement.
Yes, I understand. I have this intuition, but I didn't want to say it because I don't know how to mathematically prove it.
you are say if you have a multipartite entangled if you have a multipartite system, a tripartite system, if you say you can lower bound your tripartite entanglement by looking at the various bipartition and just lower bounding your entanglement through basically the product of these entanglements. Okay, needless to say, you should test. Say, what should you test in order to be sure of the tripartite entangled nature of your system?
Well, if it's this, the direct product is the minimum, we can just say, look at the entanglement at each one, and we have. Or, well, we have a general system that was unentangled. We have a disentangled system which became entangled. We can look at the von Neumann entropy of some partition of the system. If we have increased the von Neumann entropy, we may say that there is
but here you have a mixed
system.
Here you have a mixed state, no? So for Neumann entropy,
it's different. Yes, because you have non-zero von Neumann entropy in the beginning.
Right. So you cannot use von Neumann entropy as a reliable measure of entanglement.
Yes.
No. So the way I would do it would be taking the logarithmic negativity, okay, between say A and the joint system of B and C, for instance, then B and the joint system of A and C, and then C and the joint system of A and B. Okay, so if all these three bipartitions are inseparable, you will get certainty about the tripartite nature of your entanglement. But in your case, you have a symmetric system, so these conditions can be relaxed. Then basically, I bet that you will get somewhere in these where you have all bipartitions being inseparable. You will get some tripartite entanglement. So very nice work. Absolutely nice. So I don't want to hijack the whole discussion. So Thiago, I'm fine for now. Maybe I will have a couple of questions later on, but thank you so much, Igor, for your answer.
Sure. Thanks, Mauro. If you want to ask any more questions, just let us know. Before we move on, I just wanted to make one comment. I really enjoy your question of why entanglement, because we're always looking at entanglement here and entanglement there. But if I can say something, one of our main motivations to look into this kind of stuff, okay, of course, we wanted to show that the oscillator is non-classical, like Igor mentioned, and everything else. But these systems, they are also very nice for studying the dynamics of entanglement. So we kind of I have this intuition that entanglement works like a thermodynamical quantity. Maybe we can have some flow laws that entanglement is generated and then it goes from one partition to the other. So this was kind of exactly the kind of thing that we wanted to look into. In the end, it's ended up being a little bit different because this is a difficult question, but still, this is one motivation, I think, which is not usually mentioned, and your question is excellent because of that. So now we can move to Gabriel Landi, who is in São Paulo, and please, Gabriel, thank you for coming, and feel free to have the stage now.
Okay, thanks, Thiago. Thanks, Igor. Thanks for inviting me. So I second most of Mauro's comments. It was also a pleasure to read your dissertation, and your presentation was also very good. So I think both in terms of the quality of writing as well as the scientific content. So I mean, really wonderful work. I enjoyed it very much. Yeah, so of course, since I am a board member, I have to ask some nasty questions here and there. But other than that, I have mostly some curiosities and maybe things we could chat about. And
I'd be very happy to do that.
Yeah. So I wanted to start by actually saying that I second Mauro's comment on this obsession with entanglement. So when I was first learning about optomechanics and I saw these papers about mechanical entanglement, I was very impressed. It sounded very science fiction. it's very cool. But then after a while, I started wondering the same thing. You know, why? I mean, and I agree. So, for instance, Mauro's comment on the plot that you're looking at entanglement and then you miss out on many other interesting things. I think that's really true. And of course, I'm very biased because I like thermodynamics. So when I was reading your dissertation, I was always thinking about potential thermodynamic applications, which in fact I wanted to talk to you in a second. But I was always thinking like, wow, you're talking about entanglement, but you're kind of missing out on other cool stuff that you could also be looking on and other potential applications. So I just wanted to, I'll go into some detail of these thermodynamic applications, but I wanted to mention that I second this idea that mechanical entanglement, I don't know. Yeah. Okay, so let me start asking actual questions. So let's see. First, I wanted to ask, I will kind of make some science questions with some writing style questions about the structure of the dissertation. So I wanted to start with chapter 2, actually. I like that. Sorry, yeah.
Sorry, may I show the presentation here?
Yeah, of course, okay. Yeah.
Okay, chapter 2, Interferometer.
Yeah, so I like this chapter very much, but that's because I like graph theory a lot, and so that's very interesting to read. I wanted to ask, however, was this one thing that was not clear, and this is something that I felt many times during the dissertation, like how do the pieces connect? So I realized that you're doing a bunch of very theoretical analysis from different directions aimed at a platform for levitated optomechanics and so on, but it was not always clear how these pieces really connect with each other. So for instance, from this chapter, it starts kind of abruptly, right? You just start saying, no, calculating the transmission and reflection coefficients is hard. And we're going to introduce this method to do this. But then why? I mean, what's the big picture? So maybe can you explain to me a little bit the big picture? How is this connected to the big goal, not only of your dissertation, but actually the big goal of the lab, right? Of Thiago's lab and the whole project and so on. How does this fit in?
Well, it's because my story with optomechanics is very nonlinear. I started, okay, I want to know about optomechanics, and started learning about many theoretical topics in absolutely no certain direction. I just want to know what was this field about and what could I study. And through the time, we started studying about optical tweezers, what were optical cavities, what could we do in the classical regime, the quantum regime. And at some time, okay, we know that there are experiments that put optical cavities with some dispersive element inside. And okay, I don't know how to calculate how the light moves around within the cavity, how much light can we measure after interferometer. And so we started, let me see if we can find the image here. Probably here, optical cavities. So we started studying, okay, what would happen in the Fabry-Perot cavity, which is the most simple case. Okay, now light would bounce back and forth many times and go out of the cavity. And so when we started studying, when we started studying specifically optical cavities with membranes inside, we discovered that, okay, we could maybe associate some graph here, a very simple graph you can simplify. And then we started noticing that we have made, not me actually, who developed this method firsthand was Melvin. But when he developed this method, okay, because we started to see that this would apply to many more general and bigger interferometric devices. And all of a sudden we had, okay, we have a new method to calculating this. It was out of the blue, actually. We did not expect this. I think Thiago wants to say something.
Can I make a comment on that? Because maybe it's my fault that the thesis looks a little bit disconnected. So yeah, like Mauro said, in my mind, things work in a specific, maybe different way. In my mind, everything is connected. Like it maybe not show very clearly in the thesis, but the thing is that a little bit of history maybe is interesting. We have these weekly group meetings, where all the students get together and everybody discusses what everybody else is doing. And we wanted to, at the beginning, we were getting into this field, it was very new. We wanted to understand how to calculate the transmission of an interferometer with a lot of dispersive elements. And there's all these results from membrane optomechanics that are reported in the literature and so on. And we said, okay, we want to master this thing. And then Bruno Mello, who is a former student of mine, came up with this idea of employing directed graphs. And Igor was there, and then we started to discuss, and we said, okay, we can do this. Maybe it's related to optomechanics. It's something we need for the lab work. So let's just do that. And then it kind of was born out of this, you know, weekly group meetings that Igor started working on this. But yeah, I understand that it's not directly connected to all the other chapters that Igor worked on, but still it's a little bit the structure of the group, which I think is something that I inherited from Gisan's group. Like we had a lot of this atmosphere there that, you know, all of a sudden I was working on Bell inequalities and single photo source at the same time, and, you know, different stuff. So yeah, I admit it's my fault.
No. I mean, as I mentioned, it's a very nice result in general. I liked it very much. But I mean, yeah, of course, maybe one can. It's never easy to connect everything, right? And there's nothing wrong with making side projects which don't have anything to do possibly with the main thesis. That's fine, right? But I was just kind of curious about that. It's more a curiosity than anything else. How things fit in. So, for instance, continuing this direction. You mentioned right at the end of the chapter, you talk about the quantum version, right? So I guess, let's see where.
Here.
Yeah.
Page 35.
Yeah. So I thought this was very nice because I don't know, it really seems to connect very well with the remainder of the thesis, right? So I wanted to ask you, but it's also very short, right? You just mention it very briefly and you're done. But this connects very well with what you do later on, right? Because so did you try to connect everything? For instance, this with input-output theory that you discuss later on, or
well, at the time we were working on this, I actually did not know there was the input-output theory, okay. But I knew that there was this graph-based method that we developed. I knew that it applied for the classical case, and as I'm always wanting to see some quantum application of trying to. As I'm more interested in the quantum case, it's something personal. I try, okay, can we do this for the quantum case? And it ended up that it was a simple application, a simple translation from the classical to the quantum regime. And so, well, yes, there is not much that we say about this interpretation. The article is just a brief example, but because it was just, well, was trying to apply this to the quantum case, and very happily we could.
But if you include within this kind of graph method, if you include dissipation, then things get nasty, no?
Yes, if we include dissipation, we simply don't include some part of the output of the interferometer. The resulting this transformation is not unitary, for example.
Yeah.
So we have to be very careful in the quantum case.
Yeah, so like if you want to compute the transmission coefficient of this complicated array, but you're assuming that it's always reflection transmission, right? And as soon as there's any kind of phasing,
no imperfection, for example.
Yeah, okay. So, but in principle, input-output theory, okay, you don't get this kind of nice graph structure, but in principle, it could be used, right? You could just write down Langevin equations or something like that and really compute the transmission coefficient, no?
Yes.
Okay.
Well, dissipation you can still model. No, so you add that basically you add a beam splitter and you model it in that way.
Like the beam splitter directs something outside, something like that. Yeah.
That's basically the way you model. So the Fokker-Planck equation of say that you achieve that you can write down when you model the interaction between two modes through a beam splitter is the same, and you trace out one, is the same as what you will get by damping, by modeling it through a master equation from damping. So dissipation you can surely plug it into this framework.
Oh, that's very interesting. Okay.
Dephasing, it's a little tougher, I would say.
Yeah. Yeah. Okay. No, that's interesting. I was very curious about this. If one could extend this to open quantum systems in general. But yeah, that's cool.
We should do it.
Yeah, let's do it. I agree. So continuing on these questions about trying to understand a little bit the big picture, can you say a little bit more about living organisms? Because I mean, it's even in the title of your work, but then in the dissertation itself, it's a very short section, and it was also not very clear to me, like if there is anything really special from a theoretician point of view, like in terms of modeling about the living organism or not. So can you maybe tell me a little bit about how does this fit to the big picture? I got the impression that you want to work with living organisms, but can you tell me a little bit about that?
Well, first, if I may, first, it's astonishing that we can trap some living organism without excessive damage, without actually killing it in the first time we shine some laser into it. And so it was very interesting to see that, okay, we have some beam which have some dark focus, and we could, and so we observed that we could actually trap some living organism. Okay, but why the interest? This is why because it entered the title, because it's like I said, it's like some sci-fi technology. But why this is so important? Well, I believe it's not. I find this very credible, but I believe this is more of a research direction for the experimental part of Thiago Guerreiro's lab. That maybe we could trap some living organism in a realistic experimental. He and Felipe Almeida are actually implementing the optical bottle beam, but in the experimental implementation, I believe he can talk more about it than I can. So I don't know if this actually completely answered your question.
No, it's okay. But from a modeling perspective, it really doesn't change anything, right? I mean, it's like we have the joke about the spherical theoretician modeling a cow as a sphere or something like that. So your living organism is still a sphere, pretty much.
Yeah.
Yes, essentially.
We never made any simulations of the fact that it is actually a living organism. We just took some sphere with the dimensions of some cell, and we showed that there is a stable trapping in this kind of bottle beam. But also understanding the forces that the bottle beam exert upon a particle, even if it's already not a living organism, these forces will also act on living organisms, but it's simpler to consider first, non-living particles. This is already a huge problem. Like, okay, it's a stochastic differential equation with nonlinear force terms. So, okay, I don't need to say any more.
Yeah, of course.
To show that it's complicated. And yeah, we're also working on that, but it's very much a work in progress. And
the non-spherical nature?
Also, when you put a cell, it allows for deformations, right? So so that makes it even more complicated. We haven't even started.
And that is incredible. I apologize. It's incredibly interesting because, for instance, there are experiments, I'm sure that Thiago knows about them very well. So there are experiments currently done in levitated optomechanics where you deliberately have a non-spherical particle. And what you have is the quantization of the, say, roto vibrational degrees of freedom. And this is something incredibly hot because people are interested in sensing applications of these devices, and there are very few models of that, and they are basically done. So they are built basically ad hoc. So they wanted to. So these guys in Southampton, for instance, they wanted to build this, say, to fabricate the nanoparticle for their standard optomechanical system. But the nanoparticle was a little bit too late. They didn't realize it. They saw a strange signal, and then they realized, okay, it's elliptical, so it's not precisely round. So it's an ellipsoid. Let's see what we can learn from it. So there is a lot of physics behind it that one can exploit and can study. So
actually, that was going to be my next question, precisely about these ellipsoidal particles, because I actually worked with this during my PhD with this like rotational diffusion. It's like diffusion, but not in translational space, but in rotational space. and it's, I mean, it's even completely classically, it's already a fascinating subject. We have very few experiments on the classical rotational diffusion, and the quantum one, it's, I mean, it's mostly uncharted territory. There's so much to do there. So,
Gabriel, is that related to bird flocks?
What do you mean? Sorry.
I mean, like these models, statistical mechanics, where a bird can follow its neighbor, but there's an uncertainty in the noise.
Right. No, it doesn't. It doesn't have to be. So yeah. In magnetic particles, yes. So in magnetic particles, if they're very small, then the spins, they can just, like if you take an iron particle or something, the spins really align, and then they just follow each other together. But I think in a like a silica particle or something, it would just be the polarization degrees of freedom. Maybe it's the same principle, I don't know, but I think it's just the polarization vector which can rotate and can interact with the physical rotation, right? So we have the ellipsoidal shape, I think, creates a preferred direction, I guess, for the for the electric field, yeah.
Oh, cool.
Yeah. Okay. Yeah. So this is something I wanted to ask. So did you guys consider non-spherical particles or not yet?
Well, theoretically, no, but I know that we can simulate them numerically with the optical tweezer toolbox in MATLAB. We can say, at least numerically, we can do this, but theoretically and analytically, at least I have not.
Oh, okay, that's actually a good follow-up. So is it really that simple to simulate them? I mean, because the Hamiltonian that you wrote down, there's like some symmetries in there, right? And I think as soon as they are no longer spherical, there's probably new stuff appearing, no?
Well, I'm sorry. What we are talking about levitated particles, non-spherical indeed.
Yeah,
yeah. Okay. Well, we can. I talked very briefly here, but there is a numerical toolbox developed by the group of, I'm sorry, I forgot his name. But there is a numerical toolbox that we can just simply give all the information about the refractive index of the particle, its mechanical, its form, its shape, its density. And the numerical toolbox can give, if we input the information about the particle, information about the light beam that we want to shine into the particle, it gives the resulting vector field of force vector field. I believe Mauro wants to say something.
Just finish.
Okay, no, I just want to say that there is a very comprehensive numerical toolbox, not analytical, but numerically where we can simulate and see these trajectories, for example.
Mm-hmm.
I think it's not very easy because you see, as you said, Gabriel, the modes of motion are they can be incredibly rich. So for instance, vibrations can couple to rotation in a definitely in a nonlinear way. So all the modeling, in fact, say these guys, my friends in Southampton, are having an interesting time in modeling it in a realistic manner. But there is an element of complexity, an additional element of complexity, which is, for instance, what happens if you start driving these mechanical cavities, actually the cavity with, say, an oblate object inside, and you start driving it with a Laguerre-Gauss mode. So one of the say structured modes like those that are in chapter what is it? Chapter 4, chapter 3, I don't remember.
It's about here.
Chapter 3 of Igor's thesis, because you start having, say, all sorts of motion, because these guys feel a wavefront that is structured. There is angular momentum that you basically put into play. Is very nice, I think.
This is very nice. Actually, what Igor was mentioning was about the force, to calculate the force that acts on the object. But what you guys are talking about is the actual dynamics, right? Yeah.
So the force, okay. So that's a good point. So the force you can really calculate with this toolbox easily, then.
Yeah.
Because that's already a first step.
That's what I was actually saying. I believe I've got the question wrong. In the intermediate regime, we have. Let me see here. we can calculate from the input beam and the optical beam, we can calculate this, well, this is a spherical, what's the word, vector spherical wave functions, which we can expand some input and the input beam. And through some matrix multiplication, some this so-called tree matrix that contains all the information about the particle, we can find the composition of the outward going beam, and from different formats that affect the presentation, we can find the forces. And numerically, this is essentially very complicated, but essentially a matrix multiplication. And so the forces are relatively easy to find, but the dynamics I completely understand. That is very complicated.
I see. Okay, that's very interesting. Cool. Okay. So moving on, I have two more questions, pretty much. So I wanted to ask, most of the treatment that you do, I think in chapter 5, right, of where you considered this. Let me see if it's 5. Yeah. No, sorry, it's chapter 4. This idea that your mechanical entanglement and so on. So just so I'm sure you understand. Most of the insights that you get from those analytical calculations and so on, the way you split, like you have this unitary and you can split it into products of exponentials very nicely, so you can isolate. Yeah, so I'm looking, just to be precise, I'm looking at equation 430. Yeah. So this kind of game, so to speak, this relies crucially on no external pump, right?
Yes, here we are considering only the closed quantum dynamics of the system.
Yeah. So as soon as you add an external pump, I mean, do you have any idea what happens?
You say pump, you mean that it would be
like an external laser
driving.
Yeah, like a laser drive. It would be essentially a term which is linear in like A plus A dagger or B plus B dagger, just like a laser driving, pumping the cavity.
Yes, we'll try to increase the coherent state amplitude of each optical mode in the cavity. But I cannot tell you, unless at this moment, I can tell that this would be, as I talk about, I believe in chapter 5, how the external laser effectively acts as displacing acts as a displacement operator in the optical state. But on will this alter the generation of entanglement? I am not sure, because essentially, from one hand, the laser drive will be a local operator, but there will be a correlation between the number of photons of the cavity between the different number of photons within each cavity. I cannot say completely sure what would happen.
I see.
I think it's like adding it's not the same because but it's like adding a coherent scattering term or half a coherent scattering term, let's say, to the Hamiltonian. And this will kind of mess up we use this Baker-Campbell-Hausdorff formula like an infinite number of times. And yeah.
But from a physical perspective, I mean, you don't plan to do experiments with an external pumping. I mean, that's why you didn't include it, or
yeah. In the idea in this work was just to prepare the whole state and shut the laser down and let it evolve.
Okay. So you use the pump to prepare the state and then you shut it down at t equals 0 or something. Okay.
Yes.
Okay, that's interesting. Okay, and then finally, I wanted to mention a little bit what you finished in your presentation about these thermodynamic applications. Of course, I mean, I work in thermodynamics, so I'm very biased, and that's of course something that interests me a lot. So what I wanted to ask actually, so let me just first give a kind of opinion. I think that this kind of problem, it's actually interesting even in classical systems, even at high temperatures. Yes. You don't need to go to very cold temperatures where you have entanglement or any of that. I mean, I still think one can find very interesting applications and experiments even in a fully classical setup, because I mean, there's many discussions about how heat flows is affected by, for instance, nonlinear interactions. So if this spring lambda here, it's not a linear spring, but like a nonlinear force. there's experiments that you can do if you have more than 2 of them, and all these. I mean, I think there's a lot of stuff that can be done even classically. I'm honestly not aware of any papers. I mean, the classical transport through classical chains was a big business for theoreticians 15 years ago or something, 10 years ago. But I don't remember any really controlled experiments where you can play with these things and monitor these kinds of things. So I wanted to first kind of give this opinion that you don't need to go to entanglement here. I mean, forget about entanglement. You can go to high temperatures and still very fascinating stuff can happen. I don't know. So I don't know if you have any comments about that.
We have Wellis in the audience. He's a specialist on this kind of stuff. Maybe later he will tell us about. But yeah, please, Igor. Sorry, I don't want to interrupt.
No problem. Yes, I completely agree there. We don't need to be insert quantum entanglement or quantum effects in the systems for this to be extremely interesting, very counterintuitive. But yes, I would probably like to study the system in a classical regime. But as all my master's research was focused on entanglement, my mind immediately went for, okay, what if we put entanglement in this?
Yeah, I understand. Okay. Can you do nonlinear interactions? Can you tune the effective interaction between the 2 oscillators to be like a quartic term, like x1 minus x2 to the power 4, or something?
Well, when we consider this, as I briefly mentioned, we are considering up to a linear approximation of the electromagnetic field in the cavity. Technically, we could consider higher approximations, but it's extremely difficult to find nonlinear interactions with a Gaussian beam, for example, which we use here. Thiago actually have a paper on this, but it's a completely classical regime. It's very, very difficult actually to measure nonlinearities in Gaussian beams.
Mm-hmm. Okay. And in terms of preparation of states, you can prepare them in different temperatures, and you can, I mean, could maybe one use this to run as an engine or something, like dynamically heat them up, cool them down, and
Yeah, that's exactly what I want to see, because we could, as we just talked about, we could prepare the states that we apply a single particle coherent scattering setup where we could cool the particle. Then we would okay, you have this particle in some steady state, which would probably not be a thermal state, but we could verify how close it is to a thermal state. I'm thinking like a theorist, I'm trying to approximate through everything from thermal state of a harmonic oscillator, but we could prepare it in some approximate temperature. Then we do the same thing for the particle, and then we put the both connectors to interact, so it's coherent scattering.
Okay. Yeah, that would be very interesting to have some kind of. I see. And how would you measure stuff here? I mean, could you measure heat current? How would you characterize like?
Normally, in optomechanics, we have the fuse that leaks through the cavity.
Okay.
And through this, we can indirectly measure the position of the particles here, and from the position of the particles, we can calculate the heat that flows from one particle to another, as it was done in these nature communications.
Mm-hmm.
I don't know if I completely answer your question, but by measuring the position of the particles, we can indirectly measure the position of the particles. We can indirectly measure the heat flow from one particle to another. I see.
But it would be kind of an indirect measurement of heat flow, right? It would.
Yes. It's essentially inaccessible objects inside the cavity. Okay. You can only indirectly measure them.
I see. That's very interesting. And finally, this is my last question, I promise. Sorry for taking long. Did you guys ever consider applications in metrology? I was thinking in particular thermometry, to use this as a thermometer, but metrology more generally.
No, I have not, but this would be a good, this would be very interesting to study the application. I don't know if Thiago have thought about this before.
I have considered, but it's hard to do everything. Like, yeah, sure, we would like to, but with limited time.
Of course, yeah. As I mentioned, just a curiosity. Okay.
No, yeah, sure, but it's surely very interesting in quantum metrology to try to measure properties of the system by placing it into specific quantum states, and this would be nice.
Mm-hmm. Cool. Okay, this is pretty much what I had to ask. Again, congrats on the work. It's really nice, and thank you again.
Thank you once again.
Okay, thank you, Gabriel. Now we go to Professor Welles Morgado. He's our colleague here at PUC. Thank you, Welles.
Thank you. Can you hear me well?
Yes.
Okay, because I don't trust this machine anymore. Thank you very much, Thiago, Igor, for inviting me. It was really nice. I mean, I'm not as familiar with this kind of approach, but it was very enjoyable, and I liked the reading. And I wanted, in the beginning, I tried to do the calculations and everything, but soon it became a bit harder. But I will keep looking at the thesis because it's really interesting, and I want to get a feel for the details in the following. It was very well written. I agree with both Mauro and Gabriel. I think very few typos and stuff like that. I have collected some of them. I will send you later a copy with my observations. There's only a couple of very small things like a winner process that you keep with the same as the same process when we integrate over time and things like that. But this is not very important. So I think the small mistakes and clarifications that you could do, they are in very, very short numbers. But in order to really start to asking questions, since I have been seeing the creation of this lab from the beginning, when Thiago used to be my student, I taught him basic physics in the university, and now he's the professor there. He's my colleague, so it tells about a little bit about my age too. And it wasn't an easy thing. You got lucky with some things like economic crisis, the pandemics and everything. But it seems that it's catching on, it's going strong. Maybe you can comment about the future. What are the experiments that you are going to... first of all, let me ask you, you are going to stay for a PhD, aren't you?
Yes, I started a PhD at PUC-Rio, Thiago.
Okay, so what is the perspective from an experimental point of view in terms of what you propose now? Are you already doing measurements? How is it? Please tell me so I can get a more...
Of course. Well,
clear
I'm a
picture.
theoretical physicist. Thiago can afterwards can probably answer this better than I can. But I know that he's already performing, trying to generate the bottle beam experimentally. He has achieved some really interesting results already. And it will be very interesting. I believe he will. Let me find the bottle. It's here. I know that he's trying to. He's working out to how to make the bottle beam. But I don't know.
These are simulation results that you're showing here, isn't it?
Yes, these are completely numerical results here, right? But I don't know if it has any near future plans for cavity optomechanics, for example.
Okay. But how about the biological experiments? How is it?
Can I comment on the experiment?
Yes,
Sure,
I think you can
sure.
answer this better than I can.
Yeah.
So, experiments in Brazil are hard, but we're working towards achieving them. So the first thing, we have two lines, and one line is these tweezers immersed in fluid, in water. And this is mostly for biological applications. And where we're going now is to build this bottle beam optical tweezer and demonstrate that it's able to trap particles in a medium with a high refractive index, and then eventually do that for living cells. from a purely experimental point of view. And then there's the line of cavity optomechanics in vacuum. And then there it's a little bit more sketchy where we can give an original contribution to the field. But what I'm betting on, what we can do, which is mostly interesting, is taking these ideas of using structured light beams that we're developing for the fluid tweezers and applying them to vacuum optical tweezers. And for instance, there's a lot of work that is going on in our group on how to calibrate these optical tweezers, because these are, they satisfy stochastic nonlinear differential equations, and it's really non-trivial by measuring the data on the particle that is trapped, like position and momenta. How can you use that to infer properties of the trap? And if you can do that in an overdump regime is one thing, but to do it in the underdump regime, which is what happens in cavity optomechanics, is an entirely interesting new thing also that we plan to do. So yeah, we're working along different directions along that way.
So in order to reach that underdamped regime, you have to work at very low pressures, isn't it?
We have to work in essentially in the vacuum. Yeah,
exactly.
So
how good is that vacuum?
So what we have now is about 10 to the minus 5 millibar.
Millibar, okay, 10 to the minus 5.
This is what we have now, but we want to go to 10 to minus 8, 10 to minus 9.
Yeah.
It's like
nice. I saw some curious things in your presentation. For instance, you said that you can track the particle at picometer scale. Is it true?
Displacement resolution of about
the resolution. Okay.
Picometer, yes.
Yeah, because picometer is like hundredths of an atom, isn't it?
Yes, it's a incredibly high resolution.
It's amazing. Yeah, it's really, and femtonewtons, which is like 1 milli-piconewton, isn't it? Yeah. So, talking about this regime, I was thinking, if you're going to that low level of pressure, you have what is the mean free path for the gas? Have you thought about that?
Sorry, the mean free path?
Yes, because if you have a residual gas, can you calculate the mean free path in that case? Is it comparable to the size of the experiment of the confining region?
This can be calculated, but no, I do not know if it's comparable.
Because that could be interesting, because certainly the thermalization would be affected by that. So the kind of noise that you have to treat would become different. That could be interesting because you would not get a Gaussian noise as usual as you are using in the simulations, but maybe something else, something like maybe some correlated noise, because you could have collisions which are pretty much correlated if the mean free path is very long.
It's very long. It's like tens of centimeters to kilometers.
Yeah. So that could be a source of no Markovianity to your problem of memory, in fact.
Yes.
So maybe that's another interesting point to look at.
Yes.
I was thinking about that when that's why I asked for the gas pressure, because this is like a determining factor there. So you could get an interesting instrument to study those non-traditional sources of noise with high memory. It's another kind of correlation. I'm not saying it's quantum, but it's even classical in some sense. So it could be interesting to look at. Another thing is for instance, when you have those particles in the medium, you always neglect gravity effects. But I don't think the densities they match. They don't usually, especially if you have a gas. But if you have fluids, if you have a dielectric particle in a fluid, they don't have the same density. So you still have some kind of buoyancy, don't you? Some buoyancy effect.
Yes, but no, normally the optical force that arise in the particle, we normally have some. We'll have some the gravity pointing downwards. We normally put shine the laser beam
from below.
Yes, it is. From below. Sorry. Yes. Thank you.
Okay.
So that we have the scattering force which will counteract the gravity.
Okay. So that's how you
such that the buoyancy and the gravitational force and the scattering force that points upwards will cancel out.
That would be more important in the gas case to really do that, because if you have like a dense fluid or a fluid of more or less same density when you have water and a particle that has a density about the same, so maybe due to buoyancy, the gravity effect would be lessened. So maybe, but it's now I understand how you do it.
Yes,
so.
and when we are, for example, in water, or away from vacuum, we have actually some increase the drift on the particle, so it becomes very difficult to move around. So yes, on vacuum where we have a much lower drift, it would be much challenging.
In the case of the bottle beam, since pretty much it confines the particle in all directions, maybe the only effect would be to have the particle sit down a little lower than the symmetric point or something like that, isn't it?
Yes, probably, because normally in the Gaussian beam we have the focus of the particle, and the particle actually its stable position is a bit upward because of the scattering force. As we won't have this in the beam, well, it will depend on the medium, but in water maybe it will become higher, not because of the scattering, but because of the buoyancy.
So that's probably another advantage of the bottle beam, because you don't have to worry about this this kind of confining problem. It's already built in, isn't it? Yeah. One very interesting thing that I saw coming out in Gabriel's question. Can you go back to that reference over there? To the slide, I mean, sorry. I think
this slide?
The last ones. Yeah, that one.
Okay.
Because it looks as a very nice way of studying the importance of information versus energy exchange in a system. Because when you have this correlated system, this pretty much acts like a source of information, a source of info that can be exchanged for heat when you similarly go against the second law. So we were not really going against the second law, but can you quantify that information before and after the collisions? Are you going to try to do the experiment about that?
Just see if I get the question. If in this
I was thinking about that.
It's correlated.
Because you have some information stored in the system.
Yes.
So you have to use some of that to make the heat flow go against the second law usual path. Okay. So when at the end of the experiment, at the end of the interaction, can you quantify again that correlation? What has happened there?
Well, I don't know how to completely answer your question, but yes, we could see how much correlation there was in the different correlation at the initial and the end of the system, and we could observe that if the heat has flown from the against the second law, there will be some loss of correlation. So
you can measure that.
Yes, I believe in this article they specifically say that this would only occur if there would be some loss of correlation in the system. This specifically calculates, if I'm not wrong, the loss in mutual information within the system, such that this reversed rate flow could occur.
Ah, okay. So they have already
done.
That's
how they do it.
Yeah, in the experiment we did mutual information and Discord, but in the end of the day, it's the mutual information that matters.
Oh, okay.
I have not said this, but this is one of Gabriel Landi's article.
Ah, okay. So the author is here. Yeah, nice. I have had some trouble getting references since the lockdown started, because I have been bothering people to get articles for me. So if one of you don't mind, please could you send me the article, this one.
But this one is Nature Communications is open. So this one
it's open. Okay, yeah, so nice. I'll get that. So let me just take.
I can ask for some Russian.
Oh, I don't do that, man. I'm afraid of my computer getting some virus or something. I'm very scared of that. Yeah. Another thing I was thinking about when the subject of asymmetry came up is that you can do a spherical particle that is asymmetric in some sense, because if you have like a birefringent kind of particle, one that has a non-isotropic response dielectric constant, which is a tensorial. Can you fabricate those things? Can you make them and see what happens when you trap them?
I can't say about fabrication, about the experimental side, but I can say that there has been theoretical research on this. Asymmetrical particle optically levitated.
Yeah.
And there's some great articles by Benjamin Stickler on the dynamics of on the rotational dynamics of levitated particles.
Yes, I was thinking about that.
Asymmetry, inertial moments, different inertial moments in each axis, and it will generate some incredible effects.
Inertial, not dielectric.
Inertial moments.
Inertial moments,
not in the electric. Yes.
Yeah, I was thinking about the dielectric ones.
I don't know if there has been any research.
I was curious if you could generate some kind of torque.
For sure, someone can fabricate these particles with birefringence. Actually, one thing that I always wanted to look into, but once again, is one of these things that you have limited time. Is if your nanoparticle has a nonlinear polarizability, and you can use it to change the wavelength of the light that goes in. Maybe you could get interesting dynamics. I don't know. So if you put structure in the particle, happens.
That could be interesting. And I have a last question, which is also following a theme that Gabriel has talked about. And you say you don't have interference between the tapped particles, but can you generate those nonlinear interaction terms if you get them closer? See if you have some kind of direct interaction between them. So you could study the nonlinear springs.
When I was talking here, let me find the correct slide. One moment. That I was assuming non-overlapping tweezers.
Yeah, exactly. I was thinking about a small overlap. So
because I consider that
those nonlinear terms,
one times tweezer 2, there is no interaction here. But on the one hand, there may be some mathematical correlation, but experimentally, I don't know if the particle would be trapped and everything else. So physically, if you could do this experiment, because the electric field here would be so different from a Gaussian that I don't know. I haven't done the calculation. But maybe we could have some problem with the experiment.
Well, okay. I'm very happy. I was very curious about this and other points, but I don't want to drag too. So I'm happy. I'm very happy that you invited me. So I return the speaking baton to Professor Thiago. So
thank you, Elish. Okay, so does anybody from the committee want to ask more questions? Are you satisfied for the moment? Okay. So now I will invite the jury to a separate room so we can discuss the outcome of the defense. I think I can do this, create one breakout.
Thiago, let me just tell you, just stop the recording.
Oh, yeah.
Otherwise, the discussion is going to be recorded also.